When we hear about longevity science, our minds usually go straight to Silicon Valley. We picture tech billionaires swallowing 100 supplements a day, trying to live forever. But the real focus of this field involves something more practical than avoiding death: extending the number of years we spend free from disease, pain, and memory loss. Right now, modern medicine treats our four deadliest enemies: cardiovascular disease, cancer, dementia, and metabolic disease as completely isolated problems. We pour billions into siloed research pools, trying to knock them out one by one. This leads to the paradox of the Alzheimer's researcher, someone who spends 30 years successfully clearing brain plaques in mice, only to succumb to the disease themselves at age 94. Fighting individual age-related diseases without addressing the biological aging of the body is an endlessly reactive strategy. It's a game of whack-a-mole where the mallet always loses. This chart shows human mortality risk over a lifespan. On the x-axis, we have chronological age, and on the y-axis, the risk of dying in a given year. The line shoots upward in an aggressive exponential curve, doubling roughly every 8 years. That shaded region represents 85% of US deaths. It is the statistical footprint of our biological decay, towering over all other causes. From this perspective, cancer and dementia are no longer the primary diseases. They are the downstream symptoms of systemic cellular failure. Physical deterioration is a treatable biological process, the ultimate pre-existing condition that drives nearly every medical failure we face. Treating that condition requires us to measure biological age, the actual physical state of your cells, rather than just the number of candles on your birthday cake. Scientists have identified 12 hallmarks that drive this biological age. One of the most destructive is the accumulation of senescent cells, old, dormant zombie cells that linger in the body and trigger chronic inflammation. We already have tools to intervene. Take rapamycin. It was originally isolated from the soil of Easter Island as an antifungal compound. In mammals, rapamycin triggers autophagy, a process where the body physically consumes and recycles its own damaged proteins into fresh, functional ones. In lab trials, clearing cellular junk extends the lifespan of mammals by 10 to 15%, while simultaneously delaying the onset of heart disease and cancer. By targeting the fundamental root mechanisms of cellular aging, we can eliminate multiple diseases before they even have a chance to arise. Beyond the hardware of our cells, we can also address the software, the epigenome. This is a layer of chemical marks on top of our DNA that tells our cells which instructions to follow. As we age, these marks degrade, causing our cellular instruction manual to become unreadable. In the mid-2000s, Shinya Yamanaka discovered 4 specific genes that can effectively reboot these chemical marks. By activating these Yamanaka factors transiently in mice, scientists successfully reset the epigenetic clock, making the cells biologically younger, without reverting them into useless stem cells. This type of biological stability exists in nature. Giant tortoises have a risk of death that stays completely flat, regardless of how old they get. They do not experience the exponential decline that humans do. Longevity science aims to compress morbidity, allowing humans to mimic the tortoise by remaining highly functional and disease-free right up until the end of life. Despite aging being the primary driver of 85% of deaths, the basic science of longevity receives only about $1 per American in government funding. We treat this research with a unique double standard. While we universally champion the curing of childhood leukemia, we actively question the ethics of curing aging, citing fears of overpopulation or boredom. Placing the biological aging process into a separate moral category keeps us from addressing the single largest driver of human suffering and death. To solve this, we need a centralized systems biology project on the scale of the original Human Genome Project. Mapping this biological data is the only way to train AI systems to accurately predict and prevent the human aging process across every tissue in the body. The economic stakes are massive. Keeping the population biologically younger and healthier for just one single extra year would be worth $38 trillion to the global economy. Whether we eradicate our deadliest diseases depends on our willingness to finally fund the cure for the biological clock that drives them all.